Picture yourself standing before an engineering marvel that defies imagination. A structure as tall as a 30-story skyscraper, containing over 2 million liters of fuel, poised to accomplish what was once thought impossible, breaking free from Earth's gravitational embrace and soaring beyond our atmosphere. While this might sound like something out of science fiction, this is very much our reality. Welcome to the extraordinary world of space rockets, where human ingenuity and scientific advancement converge to create the most powerful machines ever built by humankind. These incredible vessels represent the pinnacle of human engineering achievement, combining precise calculations, cutting-edge materials, science, and decades of technological innovation. Each rocket launch is a testament to our species' determination to explore beyond our planetary boundaries, carrying with it the dreams and aspirations of generations of scientists, engineers, and space enthusiasts. Today, we're going to embark on a fascinating journey through the intricate workings of these remarkable machines. We'll delve deep into the engineering principles that make space travel possible, uncover the complex systems that work in perfect harmony to achieve escape velocity, and explore why rockets continue to be our primary gateway to cosmic exploration. From the roaring engines that generate millions of pounds of thrust to the sophisticated guidance systems that ensure precise navigation through the vacuum of space, we'll break down every crucial element that makes these incredible journeys possible. The story of rockets is not just about raw power and impressive statistics. It's a narrative of human perseverance, scientific breakthrough, and our unwavering desire to push the boundaries of what's possible. As we venture further into space, rockets remain our most reliable means of breaking free from Earth's gravitational pull, serving as the foundation for all space exploration, from satellite deployment to ambitious missions to Mars and beyond. If you're as captivated as we are by the engineering marvels that enable our journey to the stars, make sure to subscribe to Exploring the Universe and turn on notifications. By joining our community of space enthusiasts, you'll be at the forefront of discovering the latest developments in space technology and rocket science. Together, we'll unravel the mysteries of the cosmos and stay informed about humanity's greatest space adventures. Let's begin our exploration of these remarkable machines that have transformed science fiction into reality. Let's dive into the fundamental physics that make rocket propulsion possible. At its core, rocket science is based on one of the most elegant principles in physics, Newton's third law of motion. This principle, which states that for every action, there is an equal and opposite reaction, is the cornerstone of rocket propulsion, though its implications are far more profound than they might initially appear. When we observe a rocket lifting off from its launch pad, we're witnessing Newton's third law in its most spectacular form. Inside the rocket's engines, a controlled explosion creates hot, high-pressure gases that are forcefully expelled downward through the rocket's nozzles. This powerful expulsion of gases, the action, creates an equal and opposite force pushing the rocket upward, the reaction. This principle is elegantly simple, yet it's powerful enough to lift millions of pounds into space. To better understand this concept, let's consider something we've all experienced in our daily lives. Imagine holding a balloon full of air. When you release it without tying the end, the air rushes out in one direction, causing the balloon to zip erratically in the opposite direction. This is precisely the same principle that powers our most sophisticated spacecraft, just on a much grander scale. The escaping air from the balloon represents the hot gases being expelled from a rocket's engines, while the balloon's chaotic flight mirrors the directed thrust that propels the rocket upward. The beauty of rocket propulsion lies in its ability to function in any environment, including the vacuum of space. Unlike other forms of transportation that rely on pushing against a medium, like airplanes pushing against air or boats against water, rockets carry both their fuel and oxidizer with them, This self-contained system means they can operate anywhere, creating their own action-reaction pair regardless of their surroundings. The force generated by this reaction is known as thrust, and its effectiveness depends on several factors. The velocity at which the gases are expelled, the mass of the propellant being ejected per second, and the pressure difference between the exhaust gases and the surrounding environment all play crucial roles. Engineers must carefully balance these factors to achieve the optimal thrust needed for each specific mission. In practice, this principle is harnessed through sophisticated engineering. The rocket's combustion chamber is designed to create extremely high pressures and temperatures, causing the fuel and oxidizer to combust and expand rapidly. This hot gas is then forced through a carefully shaped nozzle that accelerates the flow to supersonic speeds. The faster and more massive the exhaust flow, the greater the thrust produced. When visualized, this process reveals its elegant simplicity. Molecules of hot gas rushing out of the engine at incredible speeds create an equal and opposite force, pushing the rocket forward. This continuous exchange of momentum is what enables rockets to achieve the remarkable feat of escaping Earth's gravity and venturing into the cosmos. Understanding this basic principle is crucial because it influences every aspect of rocket design, from the shape of the engine nozzles to the choice of fuel. It's a testament to human ingenuity that we've taken this fundamental law of physics and used it to create machines capable of carrying us beyond our planet's atmosphere and into the vast expanse of space. Let's explore the intricate anatomy of a rocket, breaking down its essential components and understanding how they work together in perfect harmony to achieve spaceflight. A modern rocket is a masterpiece of engineering, with each component precisely designed and integrated to perform its crucial role in the mission. The multi-stage structure of a rocket is perhaps one of its most ingenious features. Think of it as a carefully planned weight loss program for space travel. As each stage completes its purpose, it separates from the rocket, dropping away the now unnecessary weight. This staging system dramatically increases efficiency, as the rocket doesn't waste energy carrying empty fuel tanks and heavy engines through its entire journey. Typically, the first stage is the largest and most powerful, designed to overcome Earth's gravity and atmospheric resistance. Subsequent stages are optimized for operating in progressively thinner atmosphere and eventually in the vacuum of space. At the heart of any rocket are its fuel and oxidizer tanks. Unlike aircraft that can use the oxygen in the atmosphere, rockets must carry their own oxidizer since they operate in the oxygen-free environment of space. These tanks are engineering marvels in themselves. They must be incredibly lightweight, yet strong enough to contain supercooled liquids under immense pressure. The tanks are typically separated by a common bulkhead, carefully insulated to maintain the precise temperature each component requires. For instance, liquid oxygen must be kept at a frigid 297 degrees Celsius, while liquid hydrogen needs to be even colder at 423 degrees Celsius. The combustion chamber is where the real magic happens. This is the rocket's heart, where fuel and oxidizer meet and ignite in a carefully controlled explosion. The chamber must withstand extreme temperatures and pressures while maintaining structural integrity. Modern combustion chambers are built with sophisticated cooling channels running through their walls, preventing the metal from melting under the intense heat of combustion, which can exceed 5,800 degrees Celsius. The exhaust nozzle, often called the bell nozzle due to its distinctive shape, is a triumph of fluid dynamics. Its carefully calculated contours are designed to accelerate the hot gases to supersonic speeds while adapting to the changing atmospheric pressure during ascent. The nozzle's shape isn't arbitrary. It's precisely engineered to achieve optimal gas expansion and maximize thrust at different altitudes. This is why you might notice different nozzle designs for rockets intended for different missions. The guidance system is the rocket's brain, consisting of sophisticated sensors, computers, and control mechanisms. This system constantly monitors the rocket's position, speed, and orientation, making thousands of adjustments per second to keep the vehicle on its intended trajectory. It controls smaller rockets called vernier thrusters or gimbal-mounted main engines to make these precise adjustments. Modern guidance systems use a combination of inertial measurement units, GPS, and star trackers to navigate with incredible precision. The champagne bottle analogy helps visualize how these components work together. Just as pressure builds up in the champagne bottle as carbon dioxide dissolves in the liquid, pressure builds in a rocket's combustion chamber as fuel and oxidizer combine and ignite. The cork in a champagne bottle acts like the rocket's nozzle, controlling the release of this pressure. However, unlike the chaotic pop of a champagne cork, a rocket's release of pressure is precisely controlled and directed, converting this explosive force into useful thrust. Additional critical components include the payload fairing, which protects the satellite or spacecraft during ascent through the atmosphere, the avionics systems that handle communication and data processing, and various auxiliary systems for power, thermal control, and safety. Each of these systems must function flawlessly and in perfect coordination with all others for a successful mission. Understanding this complex anatomy helps appreciate why rocket engineering is often considered one of humanity's greatest achievements. Each component represents decades of research, testing, and refinement, all working together to achieve the remarkable feat of space travel. Let's explore the fascinating world of rocket propulsion systems and the fuels that power our journeys into space. The choice of propulsion system is one of the most critical decisions in rocket design, as it directly influences performance, reliability, cost, and mission capabilities. Liquid propulsion systems represent the most sophisticated and versatile approach to rocket propulsion. These systems typically use two separate components, a fuel and an oxidizer, stored in separate tanks until they meet in the combustion chamber. Common combinations include liquid oxygen and liquid hydrogen, which provides exceptional efficiency, or liquid oxygen and refined kerosene, offering a balance between performance and practicality. One of the most significant advantages of liquid propulsion is the ability to control thrust by adjusting the flow of propellants. Engineers can throttle the engine up or down, and even shut it off completely if needed. This precision control comes at the cost of complexity. These systems require intricate plumbing, powerful turbopumps, and sophisticated cooling mechanisms to function properly. Solid rocket motors, by contrast, offer elegant simplicity in their design. The fuel and oxidizer are premixed into a solid propellant, often resembling a hard rubber or plastic, cast directly into the rocket's casing with a carefully designed central core. Once ignited, a solid rocket motor cannot be shut down. It will continue burning until all propellant is consumed. While this might seem limiting, solid rockets offer several compelling advantages. They can be stored for long periods, require minimal preparation before launch, and provide intense thrust immediately upon ignition. This makes them ideal for applications like missile systems and rocket boosters. The Space Shuttle's iconic solid rocket boosters, for instance, provided about 75% of the initial thrust needed for liftoff. Hybrid propulsion systems attempt to combine the best aspects of both liquid and solid systems. In a typical hybrid rocket, one propellant is solid, usually the fuel, while the other is liquid, typically the oxidizer. This configuration offers better safety than pure solid rockets and less complexity than liquid systems. When the liquid oxidizer flow is initiated, it vaporizes the solid fuel surface, creating combustion. While hybrid rockets haven't seen widespread use in major space programs, They're gaining popularity in experimental and commercial applications due to their unique combination of safety, simplicity, and performance. The efficiency of these different propulsion systems is measured through specific impulse, ISP. Essentially, how much thrust is generated per unit of propellant consumed. Liquid hydrogen and liquid oxygen combinations typically achieve the highest specific impulse, around 450 seconds in vacuum. Solid rockets generally provide lower specific impulse, usually between 250–280 seconds, but compensate with their simplicity and high thrust-to-weight ratio. Each type of propulsion system finds its niche in modern spaceflight. The massive Saturn V that took humans to the moon used liquid propulsion exclusively, taking advantage of its high efficiency and controllability. Modern rockets often use a combination. Solid rocket boosters provide the initial thrust to break free from Earth's gravity, while liquid engines offer the precision needed for orbital insertion and space maneuvers. The future of rocket propulsion continues to evolve. New developments in hybrid propulsion systems show promise for safer, more environmentally friendly spaceflight. Alternative propulsion technologies like ion engines, while not powerful enough for launch, offer incredibly efficient options for deep space missions. Engineers are also exploring radical concepts like nuclear thermal propulsion, which could revolutionize interplanetary travel. Now, regarding the question of efficiency between liquid and solid fuels, while liquid fuel systems generally achieve higher specific impulse and therefore better efficiency, the answer isn't always straightforward. The most efficient system depends on the specific mission requirements, budget constraints, and operational considerations. What aspects of rocket propulsion do you find most intriguing? Share your thoughts in the comments below, and let's explore this fascinating topic together. Let's explore the remarkable challenges faced in rocket science and the ingenious solutions developed to overcome them. Space exploration represents one of humanity's greatest technical achievements precisely because of the complex obstacles that must be overcome. Escaping Earth's gravitational pull represents the first and most fundamental challenge. Earth's gravity is a relentless force that requires an enormous amount of energy to overcome. To achieve escape velocity, approximately 2 kilometers per second, rockets must generate phenomenal amounts of thrust. This challenge is addressed through a combination of powerful engines and the clever use of staging systems. The rocket must lift not only its payload, but also all the fuel needed for the journey, leading to what rocket scientists call the tyranny of the rocket equation. For every kilogram of payload, many kilograms of fuel are required, making the rocket's initial mass drastically larger than its eventual orbital mass. Atmospheric resistance presents another formidable challenge during ascent. As rockets accelerate through the atmosphere, they encounter intense aerodynamic forces and air resistance that increase dramatically with velocity. This challenge is met through careful aerodynamic design and what's known as max Q, the point of maximum aerodynamic pressure. Rockets are designed with streamlined fairings and must follow specific flight profiles that minimize stress during this critical phase. Engineers carefully calculate the optimal trajectory that balances the need for speed against the structural limitations of the vehicle. Temperature management represents a complex engineering challenge that must be addressed from multiple angles. During launch, rockets must handle extreme temperature variations, ranging from the cryogenic cold of liquid fuels, often below 200 degrees Celsius, to the intense heat of engine exhaust, over 3,000 degrees. The solutions include sophisticated thermal protection systems, such as regenerative cooling in engine nozzles, where fuel circulates through channels in the nozzle walls before combustion, actively cooling the structure while preheating the fuel. Additionally, special thermal insulation materials and coatings protect different parts of the rocket from both the heat of atmospheric friction and the extreme cold of space. Precise navigation and guidance represent perhaps the most intricate technical challenge. Launching a rocket isn't simply about pointing it upward and hoping for the best. It requires incredibly precise calculations and continuous adjustments. Modern rockets use a combination of advanced technologies to achieve this precision. Inertial measurement units constantly track the rocket's acceleration and orientation changes. GPS systems provide real-time position data. Star trackers offer precise attitude determination by comparing observed star positions with onboard astronomical databases. All this data feeds into sophisticated guidance computers that make thousands of calculations per second to determine the rocket's position and make necessary course corrections. The challenge of precise navigation becomes even more complex when considering orbital mechanics. Rockets must not only reach the correct altitude, but must also achieve the exact velocity and direction needed for their intended orbit. This requires perfectly timed engine burns and extremely precise attitude control, often accomplished through smaller Vernier engines or reaction control systems. These primary challenges are further complicated by their interconnected nature. Solutions to one problem often create new challenges in other areas. For instance, the powerful engines needed to overcome gravity generate intense vibrations that must be dampened to protect sensitive navigation equipment. The thermal protection needed for temperature management adds weight, which in turn requires more fuel to lift. Weather presents an additional layer of complexity to all these challenges. Launches must be carefully timed to avoid dangerous wind conditions, lightning risks, and other atmospheric hazards. This has led to the development of sophisticated weather monitoring and prediction systems specifically for space launches. Recent innovations continue to address these challenges in new ways. Reusable rocket technology, pioneered by companies like SpaceX, has introduced new solutions to old problems, such as autonomous landing systems and advanced materials that can withstand multiple launches and re-entries. Computer modeling and simulation capabilities have dramatically improved our ability to predict and prepare for various challenges before actual launches. The success of modern rocketry lies not in eliminating these challenges, but in understanding them thoroughly and developing comprehensive integrated solutions. Each successful launch represents the culmination of countless innovations and refinements in our approach to these fundamental problems. Let's dive into this fascinating question about the surprisingly large amount of fuel required to put just 1 kilogram of payload into orbit. This is one of those mind-bending aspects of space travel that often shocks people when they first learn about it. Here's the stunning truth. On average, it takes approximately 100 to 150 kilograms of fuel to put a single kilogram of payload into low Earth orbit. Yes, you read that correctly. This means that for every small laptop we want to send to space, we need roughly the weight of 2 adult humans in fuel. This ratio becomes even more dramatic for missions going beyond LEO. First, there's the massive amount of energy required to achieve orbital velocity. To reach a stable low Earth orbit, an object needs to travel at approximately 7.8 kilometers per second. This requires an enormous amount of energy, which comes from burning fuel. Second, the rocket has to carry not just the payload, but also all the fuel needed for the entire journey. The fuel tanks themselves, the engines and their complex systems, the rocket's structural components, all the navigation and control systems, the protective fairings and heat shields. This creates what rocket scientists call the rocket equation tyranny. As you add more fuel to lift the payload, you need even more fuel to lift that additional fuel, creating a cascading effect that results in these surprisingly large fuel-to-payload ratios. To put this in perspective, think about the Saturn V rocket that took astronauts to the moon. At launch, it weighed about 3,000 metric tons, but could only carry about 140 metric tons to low Earth orbit. That's less than 5% of its total launch weight. Modern rockets have improved these ratios somewhat through advanced materials and more efficient engines, but the fundamental challenge remains. SpaceX's Falcon 9, one of today's most efficient rockets, still requires about 95 kilograms of fuel for every kilogram of payload it carries to orbit. So the next time you see a rocket launch, remember that what you're watching is largely a carefully controlled explosion of fuel, with a relatively tiny payload riding on top. It's a testament to human ingenuity that we've managed to make this process reliable enough for regular space launches. What do you think about these numbers? Were they higher or lower than you expected? Share your thoughts in the comments below. The landscape of rocket technology has undergone a revolutionary transformation in recent years, with innovations that would have seemed like science fiction just a few decades ago. Let's explore these remarkable advancements that are reshaping our approach to space exploration. Reusable rockets represent perhaps the most significant paradigm shift in modern spaceflight. Traditionally, rockets were single-use vehicles, with most components either burning up in the atmosphere or becoming space debris. Companies like SpaceX and Blue Origin have fundamentally changed this model by developing rockets that can land themselves and be reused multiple times. The SpaceX Falcon 9's ability to return its first stage booster to Earth, landing either on solid ground or floating platforms at sea, has dramatically reduced launch costs. This achievement involves incredibly precise engineering. Imagine guiding a 40-meter-tall metal tube, traveling at supersonic speeds back to a specific point on Earth, then landing it vertically with pinpoint accuracy. Advanced materials and technologies have revolutionized rocket construction. Modern rockets increasingly use carbon fiber composites and advanced alloys that offer superior strength-to-weight ratios compared to traditional materials. These materials can withstand extreme temperatures and structural stresses while being significantly lighter than their predecessors. For instance, new thermal protection systems using ceramic matrices and aerogels provide better heat resistance while weighing less than traditional heat shields. 3D printing technology has also entered the rocket manufacturing process, allowing for the creation of complex engine components as single pieces, reducing weight and increasing reliability. Automated landing systems represent another leap forward in rocket technology. These systems combine advanced sensors, real-time computer processing, and precise control mechanisms to achieve what was once thought impossible. Modern landing systems use a combination of radar, LiDAR, optical cameras, and sophisticated algorithms to make thousands of adjustments per second during descent. These systems must account for varying weather conditions, fuel levels, and atmospheric dynamics in real time, all while managing the complex physics of bringing a massive rocket safely back to Earth. Ion propulsion opens up entirely new possibilities for space travel, particularly for deep space missions. Unlike traditional chemical rockets, ion engines use electrical energy to accelerate ions to extremely high speeds, providing very efficient but low-thrust propulsion. While not suitable for launching from Earth, ion engines can operate continuously for months or even years, gradually building up tremendous velocity in space. NASA's Dawn mission, for example, used ion propulsion to explore multiple asteroids, demonstrating the technology's potential for long-duration space missions. Methane-powered engines, which offer improved reusability and potential for fuel production on Mars, as demonstrated by SpaceX's Raptor engine and Blue Origin's BE-4. Advanced guidance systems utilizing artificial intelligence and machine learning to make real-time decisions during flight and landing phases. New propulsion concepts like nuclear thermal propulsion, which could dramatically reduce travel times to Mars and other distant destinations. Smart materials that can self-diagnose and potentially self-repair during missions, increasing reliability and reducing maintenance needs. improved fuel management systems using sophisticated algorithms to optimize fuel consumption and increase payload capacity. Novel launch approaches, such as air launch systems and electromagnetic catapults, which could provide more flexible and efficient ways to reach orbit. The integration of autonomous systems for in-space operations, including automated docking and orbital maneuvering. These innovations are not just improving existing capabilities, but are opening up entirely new possibilities for space exploration. The reduced launch costs from reusable rockets are enabling more frequent missions and broader participation in space activities. Advanced materials and manufacturing techniques are making rockets more reliable and capable. Automated systems are making complex operations routine, while new propulsion technologies are extending our reach into the solar system. The future holds even more promise, with developments in areas like fully reusable super-heavy launch vehicles, advanced nuclear propulsion systems, space-based fuel depots, artificial intelligence-driven mission planning and execution, sustainable space manufacturing and resource utilization. These modern innovations are transforming space access from an extraordinary achievement into a more routine operation, paving the way for ambitious goals like establishing permanent bases on the Moon and human missions to Mars. Rockets stand as monuments to human ingenuity and determination, representing far more than mere technological achievements. They embody humanity's oldest dreams of reaching beyond our earthly confines and touching the cosmos. From ancient Chinese fireworks to modern spacecraft, the evolution of rocket technology tells a story of persistent innovation, countless breakthroughs, and unwavering dedication to pushing the boundaries of what's possible. Each rocket launch we witness today is the culmination of centuries of scientific progress, decades of engineering refinement, and the collaborative efforts of thousands of brilliant minds. These magnificent machines have transformed our relationship with space, turning what was once the realm of science fiction into tangible reality. Through rockets, we've placed satellites that connect our world, telescopes that peer into the depths of the universe, and spacecraft that have touched the surfaces of other worlds. But perhaps most importantly, rockets serve as bridges between our terrestrial existence and the infinite possibilities that lie beyond our atmosphere. They are the vehicles of our species' greatest adventures, carrying not just payloads, but also our hopes, dreams, and aspirations for the future. Every successful launch represents another step in humanity's greatest journey, the exploration and understanding of our cosmic neighborhood. Looking ahead, rocket technology continues to evolve at an unprecedented pace. The emergence of reusable rockets, advanced propulsion systems, and new materials is democratizing space access in ways previously unimaginable. We stand at the threshold of a new era in space exploration, where missions to Mars become feasible, lunar bases become practical, and interplanetary travel begins to enter the realm of possibility. The story of rockets is, ultimately, the story of human potential, our ability to overcome seemingly insurmountable challenges through creativity, persistence, and collaboration. Each launch reminds us that the stars are no longer just distant lights in our night sky, but destinations within our reach. If you've been captivated by the remarkable engineering and scientific principles behind these extraordinary machines, we invite you to become part of our growing community of space enthusiasts here at Exploring the Universe. Share this video with friends who share your fascination with space exploration. Together, we can continue to learn about and celebrate humanity's greatest technological achievements and most ambitious dreams. By subscribing to our channel, you'll join a community of curious minds, exploring the frontiers of space technology and scientific discovery. Each week, we delve into new aspects of space exploration, from the latest rocket innovations to the mysteries of distant galaxies. Your engagement helps us create more content that inspires and educates future generations of space explorers. Remember, every great journey begins with a single step, and understanding the science behind rockets is your first step into the vast universe of space exploration. Like, share, and subscribe to stay connected with our latest content about space technology, exploration, and the endless wonders of the cosmos. The stars have never been closer, and with each passing day, our rocket technology brings us nearer to realizing our cosmic aspirations. What role will you play in humanity's greatest adventure?